I'm really a big fan of thin fonts on dark background. Really great for this kind of conditions. So memory management has an impact on application performance, right? So it has also an impact on application responsiveness and on system requirements. That's a reason why you should care about memory management. At least you should know the basics. And the reason for this session was that every time we have a booth at a conference and I talk to people and I ask them about garbage collection, everybody's like, yes, I know there is garbage collection. So I thought maybe it's a good idea to create a little overview of what's available and how it works in general. So in principle, and I hope you can read it, this is how the memory management is structured in the JVM. So it starts on the left side where we have the stack, right? And the stack is per thread. So and on the stack frame, we save primitives and references to objects. And then that means every thread gets its own stack frame. And if you have something like a stack overflow, that means you run out of memory in the stack frame. And this is growing and shrinking dynamically, so there is no garbage collection in this space. And because it's per thread, it's per se thread safe. And then we have the heap. And in the heap, we store all the objects, right? And the objects where we have the references on the stack, they point to the heap, right? To the objects on the heap. And this needs garbage collection. This is the main focus we talk about today. And then we have the meter space. And the meter space contains all the information that the JVM needs to handle classes. To make it very short, because we are not focusing on this part, only the center part. And if we take a look at code, and now, sorry for the guys in front, but in the back you will see it probably better. So we have this little code example here, where we have some persons, and we have a list of persons. And if we now take that to the stack, then this would be the stack frame for that thread. So each of the persons get a reference on the stack frame, and the list also get a reference here, right? And then we have the heap. And in the heap, the actual objects are allocated. These are the boxes here. And you see the references pointing from the stack to the heap, right? And also to the list. And at the moment, all these objects are live, because they are reachable from the stack. Now, if I set P1 to null, then if you would system out println P1, it would print out null. But it's still reachable because it's in the list, and the list is still live, and the list also points to this object on the heap. So you still can get the result of P1 via the list. People sometimes forget that. So if you null an object, doesn't mean it's not reachable anymore. If you have a reference somewhere in the list or in another collection, it's still live, it's still reachable on the heap. If I then set also the list to null, then it's gone, right? So then only these three center objects are reachable and live, and the other parts are just lying around on the heap, and this is literally garbage. They take up space in the heap, they are not reachable anymore, that means they need garbage collection. So someone has to pick up that stuff and clean it. That's the idea. So it's a form of automatic memory management, and it identifies and reclaims no longer used memory, and it ensures efficient memory utilization. That's the main idea behind it. And it frees users from managing the memory manually. Who did C or C++ here in the room? Who loved it to allocate memory and handle that? It can be a pain in the neck, right? So, and then we have this, garbage collection, and we have different phases in the garbage collection process. So the first phase is we have to identify the live objects. We have to find the objects that are really live, right? That's so-called tracing. If we talk about tracing algorithms, there are different ones, but literally most of them are tracing. So then we have to reclaim these resources that are held by dead objects, the garbage that was lying around, so this is freeing. And then from time to time, we have to move the live objects and compact them somewhere to get a big block of free memory. This is compaction. So these are the three phases, and that leads me to the basic principles of collecting garbage in memory. So first we talk about non-moving collectors. And the reason why they are non-moving, you will see in a little demo. So this is an example for mark and sweep. You probably, who knows mark and sweep or heard of it? Yeah, you should know that. But if you don't know, no problem, I will show you how it works. So we have this matrix, which is our heap, and the gray boxes that you see, this should be objects, right? Or memory places on the heap that can store one object in this case. Very simple idea. When they are referenced, that means when they are live, they will become blue, right? By the allocator. If the allocator allocates memory, it will be blue. After some time, it's not used anymore. Someone just set it to null or whatever. They will become purple. Purple means it's garbage. And then if they have this little red square on the upper left corner, they are marked by the garbage collector for collection. And then if they have a number in it, that just means they survived one garbage collection cycle. So every live object that survived one cycle will increase this counter. That's the idea. So the mark and sweep allocator will start allocating cells in the heap until it runs out of memory, and then it will mark all the live cells. Then it will free the dead cells, and then it will unmark the live cells and will continue. And let's see how that works. So you see, it's probably better to see on the monitors there, but we start collecting memory. And as you can see, hopefully, we have a lot of purple cells there. That means this is dead references, dead objects. Now it's full, we stop the world, we mark the cells, unmark, clean, and then again. So that goes on and on. That's the process of mark and sweep. And you see already the problem. You see it's totally cluttered. Even after we cleaned it up, doesn't mean we have a lot of free space, right? This is a simple example where every object just allocates one cell. If you think about larger objects, for example, if you need an object that has 5 cells, you need 5 free cells in a row. Could be problematic with this collector because it's really fragmented after some time. And who remembers Windows 3.11, where you have to defragment the hard drive? This is exactly what we see here. And exactly this leads us to the next collector, because that's really a problem. It works kind of, but not really good, because we have fragmentation, which is the biggest problem here. That leads me to moving collectors. And moving, you will see the difference. The moving collector, and we talk about mark and compact first. Mark and compact, the algorithm, same thing. You will see exactly the same thing as before, except when we stop the world, we mark all the live objects, we remove the garbage, and then we compact everything, defragmentation, right? So let's start this one. It's the same thing. It will stop a little bit earlier because we need some headroom for the compaction. You will see the last row will be free when it stops. And now it's stop the world, mark, remove, compact. We can start again. Right? You see the advantage. Now, even if we have a large object, we can always allocate memory. Memory allocation is in general faster with this collector because we never have to search for free cells. They are always at the end of the compaction. And that's quite convenient. You see, mark it free, compact, start again. That's the idea of mark and compact. And this collector is also used in the JVM, partly, not everywhere. Okay, that's cool. So now we know we have mark and sweep, mark and compact. Problem with this collector is we need headroom for the compaction, because you can't just copy everything to the left. You have to move stuff to the right, to the left. This whole compaction process, it takes some time. And that's the drawback of this collector. Which leads me to the next one. Totally different approach to the problem. It's a so-called copy collector. And the copy collector looks also different. We have 2 different areas, the so-called from area and the to area. And this will toggle. Every time we do a collection, we toggle the areas. From becomes to and vice versa. And we will start here in the to space. And you see we will collect. It's the same process as before. But instead of cleaning it up, we just copy all the live objects to the 2 space and just wipe out the complete former 2 space. You will see. Mark it, copy, just wipe out. And then we do the same on the right side. Once it's full, we mark it, and then and all the live objects will be copied to the other one, and it will toggle. And again, just wipe out. This is mark and copy. So we don't have to compact, it's automatically compacting, which is a big benefit because compaction takes time. The drawback here is, as you can see easily, first of all, long-living objects will be copied every time. So it doesn't matter. If you have an object that stays for the whole lifetime of your application, it will be copied every time, which is in principle not needed, but this is the way it works. And the other thing is we need twice as much memory on the heap because we have to be prepared that we need the full heap, means we need to copy the whole thing, right? Okay, so this is the mark and copy. This is all basic collection algorithms, and if we combine them, we can get to the generational collector. And this is mark and compact, generational mark and compact. And the idea behind it is that scientists figured out that most objects die young. It's the so-called weak generational hypothesis. And this is not only for Java, this is for all languages. Most of the objects die young, really hard to see, sorry for that. On the left side, you see this peak. These objects are short-living and they die shortly after they have been created. Then we have some medium section, medium-living objects, and then we have really few long-living objects. If we now tailor the whole memory management to this behavior, it could look like this. For the short-living objects, we create the so-called Eden space, right? It's a small space because most of the objects die young, doesn't have to be big. And then for the medium living objects, we use a copy collector. That's the so-called survivor spaces. And then for the long-living objects, this is a mark and compact collector on the right side. So you see it's a combination of collectors here. And that makes it possible that once objects survive a certain amount of garbage collection cycles, we can just move them to the old generation, the right side. And this one has only be garbage collected when it fills up. And this is usually really big, a huge area. So that means we have the young generation, which is on the left side. It's Eden and the survivor spaces. And we have the old generation, which is on the right side. And if we do a minor collection, we do a collection only in the young generation. And if we do a mayor collection, it's only in the old. And if we do a full collection, that means we do both. And that sometimes people mess that up. Mayor collection, full collection. Mayor collection is only in the old generation. Full collection is both, right? You have to keep that in mind. So, another demo. And this time, if an object survives more than 3 cycles of garbage collection in the young generation, it will be promoted to the old generation. Let's take a look. Okay, here we go. Eden fills up very quickly and will die. A lot of objects will die. We move them over to the survivor space, and then we continue allocating. The whole idea is we can allocate fast, right? Because Eden is small, it will be, the garbage collection won't take long, and surviving objects will be copied to the survivor spaces. They will toggle. Once they reach 3 generations here, they will move or will be promoted to the old generation. And now we will do fast forward. So we move through and you see there's some kind of a wavefront moving through the old generation, right? Because even these objects die at some point. Once this is full, we mark them in the old generation. We compact it. You will see that will happen now, probably, hopefully. Yeah. Mark it, compact, and then we promote all the objects from the young generation. And now we can start from scratch, right? So this is a full collection, which you can imagine takes time. This is what you know as garbage collection pauses, because that's what happened in the older garbage collections in the JVM. So until the heap is not full, everything's fine. When it fills up, suddenly you have to do a full collection. And that makes stop the world, copy everything around, compact, takes some time. Okay, Problem here is, if we only do a minor collection, right, and we have references from the old to the young one, how do we find them? So on the left side, we have the the young generation, and on the right, we have the old generation. So now, this is the stack frames. We do a minor GC, only the left part. We have some references hanging around. And now you see, hopefully, that the left ones are easily to find because they're directly coming from the roots to the young generation. The problem is the red one that comes from the old generation to the young generation, because when we do a minor collection, we can't see it. We don't see this reference, this one here. We can't see, I hope you can see it at all. There's an error going here. And if we do a collection here, this collector doesn't know about this reference. That means if we now just do a collection, this one will be wiped out, even if it's live. So we need a way to figure out what is a live reference that's coming from the old generation and the young one. And for that one, we have a so-called card table. That's also known as the remembered set. So that means the JVM marks this specific cell in the old generation because it has a reference to the young one. And this will be used by the minor collection, and then it knows, oh, there is another one. I have to mark this one too, and then it will work. So it's just if you stumble upon that. And believe me, it will become more complex. This is just very basic scratching the surface. So you don't have to remember all this stuff. Just remember remembered set or card table. This is sometimes quite important. This was all basic. Serial collection, stop the world. Easy, right? So what stop the world means we stop everything in the JVM, we do our collection stuff, and then we start and continue, right? That's easy. What about concurrent collection? So that means the allocator allocates memory. At the same time, the garbage collector is collecting old objects and freeing up memory. So concurrency is hard. And concurrent marking, we just talk about how to mark live objects concurrently, will look like this. So this is concurrent marking. The collector starts marking objects as reachable, and then after it was reachable, it's marked as live. That's how it works. If now suddenly the allocator decides, you know what, this reference, there was a reference here from that one down to this one, and the allocator now decides, you know what, I create a new reference and I delete this one. And at the same time where the collector is marking things live. That means because it passed already this one, this cell, the collector won't detect this one if we don't do anything. That means it continues, right? And then at some point, it will remove this cell because it doesn't know it's a live cell. So that means if everything's marked, then we have the problem. The solution for that is so-called barriers. There's also something that you might hear when you read about garbage collection. There are write barriers and read barriers. And the idea is to keep it as simple as possible. The name says it, right? The read barrier is some piece of code that will always be executed if some other piece of code tries to access a memory cell and read from it. A write barrier does exactly the same, only if you write to the cell. Right? That's the two kinds of barriers. And you have to be careful with read barriers because reading in comparison to writing happens, I think 80% is reading and 20% is writing of objects. So if you create a read barrier, it has to be very performant. Otherwise, it will drag down the performance of the whole system. That's the problem. They will be used to synchronize between the allocator and the collector. And also, if you have this intergenerational, that means from young to old, from old to young references. Read barriers are usually more expensive. Same example. So we go ahead, we mark the stuff. This is reachable. You see there's still the reference. We mark the next one as reachable. OK. And we add write barriers everywhere. This will be added automatically by the JVM. And now the collector or the allocator decides to remove this. Same thing as we saw before. But when he does it now, the write barrier will kick in. And in this case, it says every reference that was removed will automatically be marked as reachable. Right? This is just as an example here. And then that means this lower left circle will be marked, and then we have a so-called remarking phase. Until the collector is done with all the marking, it will do a remarking. And the remarking will only find these things that have been marked by the write barriers. That's the idea. And with this, you can make sure that all of this stuff will be found and marked as live. Very simple example, as I said. This is also called snapshot at the beginning, if you stumble upon this, this thing. So this is concurrent marking. Concurrent copying is the next problem, because we saw we have this compaction thing, right? Where our copy collector, we move objects around. And remember, we have references coming from the stack to the object header. So if we move the object, we have to update the reference pointing to the new address, right? So that means if we have stopped the world, this is our object, we have the stack, we have the references pointing to the header. We stop the world, we can just copy everything to a new position. We update using a forwarding pointer, we update all the references in the header to the new position, and once we are done, we remove the object and continue. Easy peasy, stop the world. If we don't stop the world, then it looks like this. We have an object, we copy it, we don't stop the world. That means suddenly this object is also accessible for all the threads. And now both objects are accessible at the same time. And that leads to the fact that threads can now write to both objects, and they do, right? So they write in one object, the other thread writes in this one, which is the correct one. How to figure that out? So we need a mechanism to mark somehow that as long as not every reference has been moved over to the new one, the old one is still the one you have to write to. And for this thing, there is one solution. There are multiple ones, but one is, for example, the so-called Brooks pointer. And the idea is, before we do the copy, we install a forwarding pointer in the object that points to itself, to the same header. Now, we can copy the whole object to a new position, and because the header is not visible now, right? So the JVM doesn't know, and also threads doesn't know about this object now. They only know this one. And nobody knows about the copy, and then we just move this forwarding pointer to this header. And from that moment on, we can update all the references. And if now some thread is writing to the left object, the forwarding header will point it to this one. And others will directly point to this one as soon as the references have been updated. I know it's complex. It gets more complex, believe me. This is easy peasy part. Once this is done, we can remove the left thing, everything's fine again. This is concurrent copying, which is used in lots of collectors. So quite interesting how that works. That was a so-called Brooks pointer. There are also other mechanisms to do that. If we now take a look at the collectors that we have in the JVM, we start with the serial one, which is the oldest one. And I try, because I started the presentation with 270 slides, right? It doesn't work for this kind of setup. So I had to strip it down. This is already 176 slides. And I have to compress it. So that's the reason for this overview. Usually I'm not a big fan of this, but that was the only way how to do it. So you choose it if you have a single core system with a small heap. Small heap means smaller than 4 gigabytes. And if you don't have any pause time requirements, then you choose the serial one. So usually it's a single-threaded application, development environments, microservices on small nodes. Nice. With this one, it will automatically be selected by the JVM if you don't select a garbage collector, and the memory is less than 1.8 gigabytes, or if you just have one CPU. The JVM will decide this is the exact right garbage collector for you. Even if you think you get G1, you get this one, right? If you don't specify a specific garbage collector. Okay, and it's not a bad garbage collector, by the way, right? So it's just, you have to know how it works. Then we have the parallel garbage collector. This is in principle the same thing as the serial. The difference here is you have to think about, you have 10 threads working on your application, and then you stop the world. Then you have one thread doing the garbage collection. This is serial. And then you continue with your 10 threads for the application. The parallel collector works a little bit differently. We have 10 threads for the application. We stop the world. Then you use 10 threads for the garbage collection. And then you continue with the 10 threads for the application. This is the reason why this is called the throughput collector, because the throughput is the highest of all the collectors. Even of the newest one, ZGC, has not that much or that high throughput as the parallel GC. Throughput means it's the relation between time you spend in garbage collection versus time you spend in the application. And this is the best thing you can do if you would like to have high throughput. This is very good for batch processing, scientific computing, or data analysis. It was the default collector from JDK 5 to 7. By the way, who's using JDK 8 in production here? Nobody. Are you sure? You heard what Vinicius said. Amazon uses a lot of JDK 8. Who's using JDK? Oh, maybe below JDK 8. Someone on 6 and 7? Not? OK. So who's using 11? Why not 17? Who's using 17? OK. 21? Some fearless people, 22? 23, early access? No? OK. Just joking. And then we have the CMS collector, concurrent mark and sweep. This is in principle the same as I showed you with the generational collector that we saw, but this is a concurrent mark. But this is exactly how it looks like. We have these different areas in the heap. And this is deprecated. So that was deprecated with JDK 9, and it was removed from the JDK in JDK 14. That means if you're on 17, you can't even select it with this command line switch. You will get an exception. It's not there. So you can choose it if the response time is more important than the throughput. So this is not really the throughput collector, right? And the pause time must be shorter than 1 second. Then this was a good collector. And it was good for web application, medium-sized enterprise systems, and so on. But it had some problems, which was the reason for a new garbage collector. And that was, like I said, deprecated in JDK 9, removed from JDK 14. And the successor of that is G1, garbage first. And this is the default collector at the moment. So if you use Java and you don't specify garbage collector, this is the one you get. Right? Oh, who's using Samaru? Or OpenJ9? Nobody? That's good, because this only applies to OpenJDK. OpenJ9 has different garbage collectors. So they behave similar, but they have different names, and they work also differently, because OpenJ9 has a different JVM implementation from IBM. This collector is different. This is the so-called region-based collector. So we saw that Eden space, survivor spaces, and then we have the old generation. This is different. If this is the heap, then we have regions, and you see on the left side, the region size depends on the heap size that you specify, with -XMX, for example. So if it's, for example, smaller than 4 gigabytes, the region is 1 megabyte, right? If it's larger than 64 gigabytes, then it's 32 megabytes, and it can't be larger than that. It can grow dynamically, but it can't shrink. So this is 32 megabytes is the largest region size you can get in G1. And the idea is you start allocating in a so-called Eden region, which, let's say, is 32 megabytes here. And then you continue with that. If this one is full, you just grab another one, and so on. And there is some ratio, like 5 to 60%, that really depends, should be young generation of the whole heap. So that means you can allocate for some time. And then at one point, we reach this 5 or 60%, whatever. And then we have to do a collection. So now we have to find the regions with most of the garbage in it. Most of the garbage means the less amount of live objects. And the reason for that is, if we just have a few live objects, we just have a few objects to copy, right? So the it's way better for the performance if you just have to copy a few things instead of copying all the stuff. That's the reason why garbage first. The regions with the biggest garbage will be collected first. So we take, for example, these 2 regions, and then we copy them in the survivor space, because all the live objects from these regions survive the garbage collection. We don't have these 2 survivor spaces, we just have 1. And then we continue, it starts looking like that, and at some point, again, we copy some stuff to the survivor space is full, then we have to promote stuff to the old generation, which is called the to-nerd space, or to-nerd region in this case. And this is how it works. Then we remove the survivor space, and so on and so on. So this is, and then in the end, the whole heap looks like that. The big advantage is we can really choose freely these regions. There's also this humongous space, right? Humongous region. This is if a region the size is larger than half of the region size of the object, then it gets a humongous region for this one. And this won't be copied. This is more or less directly to nerd space, right? But it's a specific one. So it doesn't have to go through Eden, Survivor, and so on. Okay, so this is, you see the difference. This is not the stuff that I showed you in the beginning with the demos. This looks totally different. This is a region-based collector. And all of the new collectors are like this. None of them is like the other ones that I showed you in the beginning. So, as already mentioned, this is the successor of the CMS collector. Response time is more important than throughput. It's very much the same as with the CMS, right? Pause time must be kept shorter than 1 second, then this is a good collector. For mixed workloads, even large-sized enterprise systems, one question for you. Who is actively choosing a garbage collector for his application or service here in the room? Oh, that's what I thought. Most of you just go with the default, which is this one, which is fine. It's a good collector. It's just interesting that we have all these collectors, but most of the people just go with the default. That means the JVM team did a good job, right? Because it seems to work. OK, this is the default collector from JDK 9 onwards. So even today, it will change in the future. And that leads me to epsilon. Who knows epsilon? Someone ever heard about that? One? Yeah, it's an interesting collector. It's the no collection collector. It doesn't do anything. There is no garbage collection here. Does it make sense? It makes sense for some specific use cases. For example, if you would like to test your application performance, pure code performance, and you use a garbage collector, then always the garbage collector will be part of the measurement, right? Because you have no influence on when the garbage collection will happen. If you would like to get rid of the garbage collection at all, you have to use this one. Problem here is, if it's full, the heap, it's full, right? That means if you have no idea how much memory your application is using, you will run into a lot of out-of-memory exceptions. So that's the drawback with this thing. You don't have any garbage collection, but you need to know how much memory you use. Also, if you only do testing. This is also useful if you really need the last drop of latency or throughput, because if you don't have any garbage collection, you can't go better than this, right? But as I said, you need to know your application. Anyway, if you choose a garbage collector, first of all, measure your application. You need to know your code, how it behaves, and then you can choose the right collector. Just don't trust anybody who says, Netflix is using this one, we use it too, yay. Yeah, we saw that with microservices. Now everybody's using microservices. It's only in builds of OpenJDK, so OpenJ9 doesn't have anything like this. So, but as we saw, nobody uses OpenJ9 here anyway. Next one, Shenandoah. Who knows that one? Oh, a few more. Probably the Red Hat people here. Because this collector was created by Red Hat. And it's the first of the publicly available new collectors, I would say. So it's still region-based, and you can choose it if your response time has high priority, right? You need a very low response times, responsive application, and this is a very good collector. It's also good for very large heaps and predictable response times. So I think the limit is 10 milliseconds, if I remember right. So they tell you that garbage collection won't take longer than 10 milliseconds. That's guaranteed. That's good, right? This is a concurrent collector. If we think about it, first of all, it sounds great, right? So it runs at the same time when the application is running. But what does it really mean? That means if you have 10 threads, to keep the same example, running for your application, right? So then the 10 threads now will also be used for garbage collection at the same time. That means you might have 8 threads for your application, and 2 threads will always doing garbage collection. What does it mean for performance? It will be lower than with the other collectors. That's something you have to keep in mind. So performance will always drop if you do concurrent collection. And the reason is obvious. So this is good for latency-sensitive applications, large-scale systems, highly concurrent applications. This is a fully concurrent collector, but it's not generational. It just has one generation. At the moment, I'm not sure if Roman is working on a generational version. I think there have been plans, but never made it to OpenJDK yet. So another thing is, this is not available in Oracle JDK. Who's using Oracle JDK here? I don't. Oh yeah, one, Alina. but this is GraalVM. This is a little bit different. I mean the pure Oracle JDK, probably because Red Hat invented it. Oracle don't support it, but it is in OpenJDK. So if you use OpenJDK, you can use it. So it's no problem. You have a little bit reduced throughput, and it makes use of this barrier concept. I will come to that. And it will be complex, believe me. Then we have ZGC. And this is wrong. The Z doesn't stand for 0. It's just, but yeah, it's ZGC. That's the latest and greatest garbage collector that we have in OpenJDK. Again, it's a region-based collector. So we have young generation, old generation. We start collecting stuff in the, allocating stuff in the young generation. When they get old enough, when they age, they survive garbage collection cycles, they will be promoted to the old generation. We don't have survivor spaces here, right? We only have young and old. And it's not really 2 separate spaces. It's mixed up in one big space, so it looks like this, more or less. That is very much simplified. OK. How does it work? I will come to that in a second. This is even faster than Shenandoah, so they can go below 10 milliseconds easily with garbage collection cycles. This is a generational collector, which is always good for performance if you have generational. Because the problem if you have non-generational, that means just one generation, that means you fill up everything, then you have to clean up everything. You fill up everything, clean it up. So if you do generational, you can allocate and then promote stuff. And then after some time, you have to also do the collection in the old generation. So this is usually for performance reasons. Generational collectors are always better than non-generational ones. So this is for very large heaps. And if I say very large, I talk about terabytes here, right? And then still with this very low pause times. So yes, there are still something like stop the world pause times, but they are so small that you can ignore them. It's maybe 3 milliseconds. This is more or less OK for most of the applications. So this is for low latency sensitive applications, large-scale systems, highly concurrent applications. And it will become the default collector in the future. So that I don't know from which JDK on, maybe 23, this will be the default collector for you. And everybody who's a Netflix fan, yes, you will be like Netflix because they use it too. Right? And they made some tests, and they figured out that they got a drop of 3% in performance by using ZGC in their application. Doesn't mean it's your application, right? Keep that in mind. You are not Netflix. So yeah, the non-generational version will be deprecated. So just, by the way, I'm a big Netflix fan, even if it doesn't sound like. Then that leads me to the last one on the list, which is our own collector, which is C4. And the reason why I didn't really spend a lot of time in the ZGC is that ZGC is more or less a copy of this one. And we did that already 10 years ago. So, and it's very much the same. The non-generational ZGC is exactly the same algorithm that we use in C4. And this is part of the Azul Zing JVM. And it makes use of the loaded value barrier, which is a read barrier. And remember, I told you have to be very fast when you do read barriers to keep up the performance. And this also applies for ZGC. If you use it on Linux, use transparent huge pages. The collector really benefits from the performance. And this is also the same for ZGC. That's why I just mentioned it here. So if we have GC threads, hard to see on this one, I hope better on the screens, and they access the root objects or the root frames here, the stack frames, to find live objects, right? So we mark objects by finding new ones, we mark them live, and so on. And now at the same time, the allocator starts allocating an object. How does the collector know that this object now is live? Well, the big trick here with these collectors is that the allocation thread can also mark objects as live. And that's the big difference. And this is done by using the read barrier. So we have the read barrier on each of the memory accesses. As soon as the allocation thread accesses the memory cell, the read barrier will be triggered, and it will mark the cell as live. So the collector doesn't have to. So the collector and the allocator work hand in hand. That's the big difference here, right? So and how it's done, we call it test and jump. And I think in ZGC it's called colored pointers. That's what we call LVB, or loaded value barrier, but it's the same thing. So the only thing we have to do is, in the read barrier, we check, is it a reference, is it live, and mark it. If it's not live, we will come to that point. And then it will be passed to the garbage collector, right? So this is, and then the garbage collector doesn't have to take care about it. So every cell has just be selected once. You don't have to go in this remarking phase. Oh, this is quite complicated. If we do remapping, that means updating all the references, the other GCs on top and the C4 or ZGC on the bottom, then it's like this. So the first time we copy the header of the object, and what the other garbage collectors do, except ZGC, they create a so-called forwarding pointer, right? And then they have to update all the references. So what we do, and also ZGC, we copy the forwarding information somewhere off heap. And this is always the same place. So what happens then is, once we update it by the read barrier all the references, and if now the application thread tries to access this object, which is not there anymore because it's now here, it does the test and jump. Is it a reference? Yes. Is it live? No. Look it up here and update the references. And then everything is, so again, the allocation thread is also changing and marking things, right? And that helps. And once this is done, we can just remove the original object from the physical memory, exactly at that point, where the other collectors have to first update all the references because the information is in the forwarding header, and this is still in the old location. They have to wait until all the references have been updated. We don't have to, because we have the forwarding information somewhere off heap, and ZGC the same. So this is faster, it's so-called quick release. All right, this is the same as ZGC. It's for low latency systems, large-scale systems. We have, for example, one customer, and they working in high-speed trading. They have a 21 terabyte heap. When I heard that the first time, I was like, what? How big is the machine? I mean, 21 terabyte, and this is only heap. You need more memory, right, for the operating system and so on. So this is only available in Azure Zing. And the difference, the real difference that we have is we don't have the performance problem because we have a different compiler which creates faster code than the one in OpenJDK. That's the reason why the system, when you use Zing, it's still faster as if you would use OpenJDK with ZGC. OK, the question is which one to choose. We have three criteria: throughput, latency, resource usage. Unfortunately, you can only choose two. So either you choose very high throughput and it should very low resource usage. Sorry, latency won't be low, right? So you have to choose this stuff. And to make it easier for you, there's a little chart that can help you figuring out. We have the pause times increasing to the right, and we have the runtime overhead increasing to the left, and then you can choose which might be a good collector for your application. But that means you need to know your application. That's the first thing you need to do. Monitor your application, know the memory consumption, how much performance do you need, and all these things. And then you can choose the right garbage collector. There is an overview, and probably the slides will be provided by the conference, I hope so. Then you can find also some information in one table, which is easier. And with this, I'm done, and we have still 3 minutes left for questions, if there are any. Yes?
What happens when there's the copy of the references and the thread still accesses your object because it hasn't been forwarded yet, but it changes the value? Hasn't the value been copied already?
The question was, what happens if you copy an object and then the application accesses the old object and try to change it, right? So this, if you talk about the ZGC, for example, this will be prevented by the by the value barriers here, by the read barriers. So you can't write to it until it's copied. So it will do the copy first, and then it will change the value. So they take care about all of these problems. Any other question? Yes.
Yeah. Also regarding barriers, I came here a little bit late, so it was hard for me to follow. I wanted to understand better the concept of right-read barriers. I know barriers from like threads. Where they're like a synchronization point where data continues when all the threads like arrive at that point, right? And I try to correlate with this concept of
Okay.
read and write barriers.
So the question was about read and write barriers.
Yeah, it was about read and write barriers because I try to correlate with normal barriers, but I think
This is a little bit different. So you can think about, like I said, the read and write barriers is a piece of code that will be executed when you try to either read from the memory cell or write to the memory cell. Then first this code will be executed, whatever it is. This is up to you. It's up to the garbage collection creator.
does it have nothing to do with
It's not like the JVM save points, which is something similar, where you stop all threads. No, this is something different, yeah.
Yeah, so then we use like I think the right barriers to know to make the collector knows that there wasn't
Yes.
an object.
Yeah, so the write barriers and read barriers are used to communicate kind of between the collector and the allocator to make sure that everything's in place. Okay, any other question? Yes, over there.
Hello, thank you for your presentation. My question is, considering that I have a microservice, really small one with one CPU and 1 gig of RAM, by default you use the 0, right? So my question is, in case of like really concerns about latency, and I receive many requests, which one is the best?
Okay, the question was, if I have a microservice that's really small, has 1 gigabyte of RAM, and usually you will get the serial collector, and now you think about how can I use another one and make it sense or not? You can try, but I can't really tell you that this is really beneficial, because the other collectors, first of all, most of them need more CPU performance, more memory. So that's the reason why serial is still a good collector for these kind of things. So, and now, unfortunately, we're running out of time. So, yeah, if you have further questions, I will be right at the back of the room, and then we'll be able to answer your questions. Thanks for attending.